All right, in this video, we are looking at the contrapositive of the Pythagorean theorem. And so what we have up here is we have the Pythagorean theorem, but we have it written as a conditional statement. So if a triangle is a right triangle, then a squared plus b squared equals c squared. We know this relationship only holds true for right triangles. One way I want to kind of think of this, if I had a length of a on the triangle, and I did a times a, or a squared could be represented by the area of that square. And if I had a side length of b, and I made a square off of it with another side length, we know that the area of that square could be b squared. And then finally, if I did the same thing with my hypotenuse, and I know I'm kind of overlapping things here, that if we had a square that had side length of c, that base times height for that square would give us an area of c squared. And what the idea of the Pythagorean theorem is, it can be represented with what's called an area model, where we know that this area, the area of that square, a squared, plus the area of this square, b squared, would be equal to the area of that square off the hypotenuse, c squared. And so what I want us to think about right now is, what is the contrapositive of this? Hopefully we can kind of remember what a contrapositive is. And here's what it is. It's whenever I interchange the hypothesis and the conclusion. It's when I interchange these two and then I negate both of them. So basically what it's saying here is, if a squared plus b squared is not equal to c squared, I notice I negated that statement. If it's not equal to c squared, then the triangle is not a right triangle. And where we're going to go in this unit is in this lesson is we're going to see, what can we tell about the triangle? We might know it's not right, but are there other things that we can deduce? And so the question is, what do we know about triangles in these three situations? This is the case that we've examined, a squared plus b squared equals c squared. But what about when a squared plus b squared is greater than c squared? What about when it's less than c squared? And so in order to examine this, I'm going to bring in another thing for us to look at. So I've got this website. This is a GeoGebra applet here. And what we see is we have that same area model as I've shown you. So let's say this is a squared, this is b squared, and this is c squared. So we have a little square at the area of 16. So maybe this is like a length of 4, and this is a length of 4. And then we have a area of 36. So suppose this has a length of 6, and this triangle has a side length of 6. Well, then over here, this has the area of the square root of 52, because this square's area, 16 plus 36, equals 52. Now, our first case, if we kind of remember back here, is let's examine what it looks like when a squared plus b squared is greater than c squared. So if I come back over here, what if this plus this, what if those two areas are greater than this? What can I conclude? Well, let's see. Notice as I kind of take this vertex and drag it this way, notice it kind of expands the size of this square, and then this square off the hypotenuse kind of got smaller, didn't it? Notice what happens is I change this. Notice as we go from kind of having this Pythagorean relationship of a right triangle, and I come this way. Now you notice, well, maybe it looks like this square and this square together would be larger than this square. Notice we went from a right triangle. We went from a right triangle to an acute triangle. Then a squared plus b squared was greater than c squared. That's this second relationship. So this relationship would hold true for an acute triangle. And once again, we can look at it by, let's say I kind of go back to having my right triangle. Change that back to 90 degrees. What happens if I play with this one? Notice if I move this up and kind of make it more acute. Once again, it kind of reduced the area of this square off the hypotenuse and kind of increase the area of the square off this leg. So by doing that, a squared plus b squared is greater than c squared, because the area off that hypotenuse looks like it's less than the sum of these two areas. So we can assume for this second case that if a squared plus b squared is greater than c squared, that's only going to be true for an acute triangle. And then you might kind of already be putting the pieces together. What about if we say a squared plus b squared is less than c squared? What if this area plus this area is less than this area? Let's see what it looks like. How can we make a triangle that has a much larger area right here than these two? You might be thinking, okay, well, if I drag this vertex down and make it an obtuse triangle, you can see that, oh, the area on that hypotenuse kind of grew, and these two areas kind of got smaller. So here, this area plus this area would be less than this. If a squared plus b squared is less than c squared, we know that our triangle is going to be obtuse. And you can see here that we have an obtuse triangle. And I could do it by moving my other vertex as well. If I go back and reset it, if I kind of move vertex B over, once again, I could do something like this. And we can see here that the area of this little square plus the area of this little square is much less than the square off of what was previously the hypotenuse. You can see here it's got the kind of the math worked out for you. 11 plus 36 is way less than the square root of 84. And so that's what you can kind of deduce on this third row here. If a squared plus b squared is less than c squared, we know that's obtuse. So our first case is a right triangle, our second case is an acute triangle, and our third case is an obtuse triangle. So I think I have it summarized here on the next slide. Let's see. Yeah, that's what we got right here. We know that if a squared plus b squared is greater than c squared, we have an acute triangle. That would be a triangle like this. And if a squared plus b squared equals c squared, that would be a right triangle. And then lastly, if a squared plus b squared is less than c squared, if the square off that hypotenuse is really big, or off what was the hypotenuse is really big, we know that we'd have an obtuse triangle. So these are our three cases. So basically we can tell more than just whether or not it's a right triangle with the Pythagorean theorem. We can tell whether or not it's acute or obtuse as well. And so here's kind of some practice question. It says, classify the triangle with the given side lengths. So let's work this out. We're going to do a squared plus b squared, and we're going to see if that's equal to c squared. So for this first problem, we're going to use our two shorter sides, a squared plus b squared, and we're going to see, we don't know if it's equal, so I'm going to put a little question mark over it. We're going to see how that compares to 11 squared. And what we have is 36 plus 36, and how does that compare to 121? Well, you probably see that 72 is actually much less than 121. So in this case, a squared plus b squared is less than c squared. And you're thinking, okay, well, what do we know about this? Well, hopefully you can conclude since a squared plus b squared is less than c squared, a squared plus b squared is less than c squared, this is going to be an obtuse triangle. Now, I'm kind of running out of room, but I'm going to kind of separate it, and we're going to do the second question here. Here we have, if we have a squared plus b squared, and we're trying to compare it to c squared, we have 4 squared plus 5 squared, and we're saying, okay, well, how does that compare to 6 squared? Let's do the math. Well, here it looks like 16 plus 25, I think that would be 41, and that's actually greater than 36. So here what we have is we have a situation where a squared plus b squared is greater than c squared, and in that situation it would be acute. We know we've got an acute triangle. And now if we were to do this last one, well, honestly, if you were to do this last one, you'd probably jump into it and you'd start thinking, okay, well, how does a squared plus b squared compare to c squared? And you do a bunch of math. But we have to remember, here's our triangle inequality theorem. Okay? What you recognize, if we remember back to a previous lesson, is that these aren't even side lengths that could make a triangle. This is not a triangle. So it's kind of like a none of the above. Don't forget about our previous lessons. Right here, if I'm looking at this, if I add 4 and 5, imagine a length of 4 and 5, well, that's not going to be able to make a triangle with a length of 9. What you learned in the triangle inequality theorem is that in that, the two shorter sides actually have to be greater than the length of the third side. In other words, 4 plus 5 would have to be greater than 9, and that's not the case here. So, yeah, was question 3 a trick question? Yeah, it was, but you'll make it.